All right, perfect. So, all of you all are doing, a really big variety of different things. Uh, and what I'm going to be talking about might be familiar on different levels. So I'm going to start off real basic, and then we can jump into the specifics depending on how much we want to cover. The fundamental reason we are able to do any of the things we're doing is that galaxies look very different when you look at them at different wavelengths, at different parts of the electromagnetic spectrum, right? So the same galaxy, seen in the infrared with Spitzer, seen in the optical to like near infrared, so like slightly red wavelengths with Hubble, or seen in the X-rays with Chandra, look extremely different, right? Like, so this is the same object you're looking at, but the sort of presentation of this galaxy looks very different. And the reason this happens is because although you can think of the galaxy as a whole radiating light across the electromagnetic spectrum, the precise sources that are responsible for emitting light at a given wavelength or at a given frequency or at a given energy, these are all interchangeable. You can use whatever you're comfortable with. Change depending on which part of the electromagnetic spectrum you care about. So if you think about the highest energy things, the things that are emitting gamma rays are going to be different from the things that are emitting ultraviolet radiation, are going to be different from the things that emit optical or infrared or radio emission. And the study of galaxy spectra or galaxy spectral energy distributions, or SEDs that we like to call them, really depends on sort of which part of the spectrum you're interested in and what are the sources of emission that are putting out energy at that particular wavelength. So if you look at it across everything, across basically the whole electromagnetic spectrum, the sources that are contributing to emission at, say, the ultraviolet versus the optical versus the infrared tend to be things like light from stars of different temperatures, or light from, basically, when light from stars passes through clouds of gas, it sometimes ends up exciting the elements in the gas, and then as these elements jump to higher levels and then they come down and they emit photons, you can see some of that emission. Or sometimes light just gets scattered and absorbed by grains of something called interstellar dust, which basically is made of the same material that you find in car exhaust. So if you look at the exhaust pipe of a car and you see this black sooty material, uh, there's something called there's something like astronomers will talk about and call dust. That is basically just these carbonaceous and silicate based grains that tend to scatter light or absorb and like re-radiate it at much higher wavelengths or much lower energies. And so the sum of all of these together will give you this, basically this black looking line, which you call the spectral energy distribution, or sometimes just the spectrum of a galaxy. So uh, in short, if anyone says, oh, I looked at a galaxy's SED, all they're saying is that they looked at how bright the galaxy is at different wavelengths, right? Is that clear so far? Good. So now let's jump here a bit. So this is sort of showing one example spectrum, right? And this is going from so here the x-axis is wavelength in angstroms. So 1 angstrom is 10 raised to minus 10 meters. And the y-axis is flux density. So flux density is basically something you're talking about when you say, I have a galaxy, it's emitting photons, right? And then these photons are spreading out isotropically in a shell, right? And so if I'm at a certain distance away from this galaxy, and I'm essentially looking at the amount of light that's coming on my telescope's detector, basically like a small patch of the sky, then what's the amount of the total flux that's coming through that uh, small receiver? And so that essentially gives you the flux density in these really weird units called microjansky. When people talk about fluxes, they'll use all sorts of units. Some people will do ergs per second per centimeter square per angstrom or per hertz, uh, or some might even convert it to absolute luminosities, which is just how bright the galaxy is instead of flux. Observer-friendly units are fluxes because this is like what you measure from a telescope. But theorist-friendly units are luminosities because they've already gotten rid of, observational systematics like how far away I am from the galaxy. So these are all slightly technical, but basically you will find plots of galaxy SEDs that have a whole range of different units for the y-axis, right? So x-axis, you'll find one of three units. You'll find wavelength or you'll find energy. So people might report the x-axis in electron volts, or you will find frequency, right? So the x-axis is one of these three things. The y-axis can be a bunch of different things, but they all are some variation of basically how bright is the galaxy at a given wavelength. Right? So I think the fundamental thing is understanding that it's just that it's a measure of how bright a galaxy is.
Right.
Now,
And I just wanted to add that the flux density, so that's the physical, if you want to, unit will be its power per area per unit frequency, right? So
mhm,
it's watts per meter squared per hertz. So if you think of like a light bulb, that's giving the luminosity of that light bulb is in watts, like it's a 100-watt light bulb. But then what is the light that is being emitted a certain distance away on a wall? So that's watts per meter squared, right? And then at what frequency, right? So because it's going to be different amount of light at different frequency. So at this hertz, so it's watts per meter squared per hertz. That's what this Jansky is.
yep, perfect. And like I was a theorist who had never seen a unit before coming to astronomy, so it took me a really long time to, get used to all of these like really weird units. And so make sure like you take your time to understand that properly. There are a lot of subtleties in how you convert flux density given in one form to another form. And even now, like adult as astronomers who've been in the field for 50 years will still make mistakes. So like don't be hard on yourself for that. But just ask, talk to people, make sure you double check your calculations. Okay, so we normally don't see the whole spectrum depending on which telescope we're using or which facilities we have access to. You might only see like a part of this, and you might either see it in terms of uh, photometry, which is where the way you have filters that you can put on top of your camera or telescope to block out everything except a small range of frequencies. Like imagine putting a red, green, or blue filter in front of your camera. That's going to block out all the other frequencies so that you only get your photograph in shades of red, blue, or green. You have many such filters that you can put in front of a telescope to isolate the light that's coming from a small region in frequency or energy space. And so that's what these things on the bottom are. These are all photometric filters. These five are in the optical range, and then all of these are in the infrared. So you can have filters across a whole range of different frequencies. If and what a filter does is it basically says all the light that's coming in that range, I'm going to collect, and I'm going to make one picture of how bright the galaxy is, uh, averaged over all of these wavelength ranges. So you're not probing the whole spectrum anymore. You're basically taking snapshots of the spectrum at a bunch of different frequency ranges. Now, these filters can be divided into three categories, which is just broad, medium, and narrow. So broadband filters are basically filters that allow for a very wide range of wavelengths. So here, let's see this filter. This is IRAC channel 1. So that's with the Spitzer telescope. And so this is 10 raised to 4 angstroms or 1 micron, 2 micron, 3. So this is everything from the 3 to 4 micron range, basically. So it's saying that like this point is an average of how bright this galaxy is over this whole range of 3 to 4 microns, right? So that's a broadband filter. So that's a uh, it has a width of zero point 0.1 microns, or uh, comparatively, a medium band filter will have a width that's somewhere between 1/20th to 1/50th of this range. And then a narrow band filter will have an extremely narrow transmission range. So it can be sometimes as small as 10 angstroms, or like 1 nanometer in, exactly. So the reason we have broad, medium, and narrow bands is that broadbands require the least exposure. If you want me to like skip over these things, let me know. But like,
No,
I'm
no,
just
these are good for us. I mean, this as observer, this is what we work with. Yeah.
right. So if you think of it in terms of like, I'm going to point my telescope at something and look at it, right? I need to collect some amount of light. And once I have enough light, I have an image. So in terms of, I guess, actual numbers, you define this in terms of signal to noise, right? So your noise is what happens when you just look at a blank patch of sky and you're recording essentially uh, random fluctuations in your sensor. And as you look at a particular astronomical object, photons from that object are coming into your telescope, and more of these accumulate until you have enough signal, right, to beat out the noise and to actually show you a picture of the galaxy. Now, if you have a broadband filter, then you're essentially saying, I'm going to smear out the spectrum, right? Like this. I'm going to just get a very coarse view of what's happening. But the amount of time I need to get enough signal to noise is much lower than if I use a narrow band or a medium band filter, just because I'm now allowing photons from a whole wide range of wavelengths to come through.
Mhm.
But if I have a medium band filter, I'll be able to probe some of these finer features. Oh, I can draw. So yeah. So if I want to like get these like two peaks that correspond to emission from a particular element, then I can use a medium band or a narrow band filter. But if I have like a very narrow filter here, sorry, I can't draw a straight line apparently, but then it'll take a lot longer for the same amount of photons to accumulate in my camera's detector. So
Mhm.
that means that I need to keep the telescope pointed at that object for a much longer amount of time.
Yeah.
So for that reason, broadbands are basically the cheapest thing you can do in terms of telescope time to get pictures of a galaxy. That's the easiest thing you can do.
Hmm.
Uh, then the next easiest thing to do is to use medium band filters. And then beyond that, if you want to probe the spectrum in like all of its exquisite detail, you go and actually get a spectrum. So instead of using these filters at all, you put a diffraction grating or something that basically like takes the light and splits it like through a prism to separate it into all of its component wavelengths. And then you record the intensity at each wavelength and you get a measure of the spectrum. So that's the most expensive thing you can do. And so what ends up happening is we usually get a range of different observations of the same galaxy. Uh, the first observations to come are usually the cheapest, and so they are usually this broadband imaging. Then if we find something interesting with just the broadband features, we're like, oh, okay, there's something in just the black points that looks unusual, or that looks difficult to explain or looks interesting. Then we will follow that up with either medium bands or with a spectrum,
Hmm.
right?
Yeah. So I can just
Yeah.
I'll just summarize again because these are all very, very important points that will that you will be dealing with, right, in your project. So in astronomy, there are two types of observations that you will always hear. One is imaging, and the other one is spectroscopy, right? So when you do imaging, you're getting light, and the art of extracting the light, finding out how much light is in what object, is called photometry, right? The so what you get from doing imaging is like so photometry is where you are calculating what is the total amount of light coming from this object, what is the total flux of light coming from this object. That's called performing photometry, right? Photometry is how much light, the flux that you're getting. Or you can get but when you're doing photometry, you don't really know what wavelength that light is coming from. I mean, if you know what filter you have observed in, then you know what wavelength that light is coming from, right? So that there are many ways by which you can do this photometry, as Karthik was saying. So you can say that I don't really care about what wavelength this light is coming for. I just want to collect as much light I can get from this object. So then you're agnostic about wavelength, right? So you put a very wide filter, right? Filter is something that like as the name suggests, it filters out some objects but allows and other things through, right? So if you have an extra wide filter, that means that you are just allowing light from every wave, all different wavelengths to come through. So let's say I have a wide filter in so JWST, you will see there are these filter names called W2. Those are the wide filter, extra wide filters. So it's every light between, let's say, zero point 0.9 micrometers to 2 micrometers, you're just allowing that light to come through. You're not picking and choosing. You're being very acceptable of all types of lights, right? If you are actually not int you're if you're interested in the color, right? If you actually want to know, is this galaxy young or is this galaxy old? Is this galaxy dusty? Does this galaxy have star forming regions? If you're asking about this type of questions, then you want the color information. Then you want to differentiate between the blue and the red region, right? Between your zero point 0.9 micrometer and your 2 micrometer. You don't want all that light to be mushed together. You want them separately, right? So then you will put a filter that only allows light around zero point 0.9 micrometer through. And then you will put another filter that only allows light around 2 micrometer through, right? And then you will be comparing between those two lights to tell you what's happening. So those are the wide filters that so those are the filters that you can have, like medium band or wide band. What those num are telling you is that how much light it's allowing through. So the narrow filter, that's it's extremely small wavelength range is allowed. Medium filter, a slightly wider filter range is allowed. Wide filter, an even wider filter range is allowed. And then extra wide is pretty much like all your telescope can gather, right? Um, but then,
And huge examples of like medium bands, for example, you can see the difference, right? So these are like wide filters, the orange and the pink and the blue, and then all of these colored lines are medium band filters.
so they allow even shorter wavelength range, right? But then sometimes you actually want even finer information. So when Karthik was showing the SED, you can see that there are all these little lines, right? Different lines. And sometimes those lines are so close to one another. Like there is that in the center, I think, there are two lines that are very close to one another, that even if you put a narrow band filter, it's still the light from those two lines are gonna come through the same filter. You cannot differentiate, right? So what do we do in that case when your imaging is not able to differentiate? What would you do? Any idea? What's the next step?
Spectroscopy.
Spectroscopy, right? So that's when you will whip out your spectroscopy, because you want to actually do even finer differentiation between wavelengths of light, right? So a spectra is it's giving you, depending on how fine the spectroscopy, or your spectroscope is, it's gonna give you light per wavelength, right? And you will hear words like R equals 100, R equals 1000, R equals 10,000 spectroscopy. What that means is that it's able to differentiate. So R equals 100 means that it can differentiate between yeah, so there I think Karthik is pulling up over there. It just tells you like how fine of a grid that is, like, like, can you differentiate between 1 nanometer, or can you differentiate between zero point 0.1 nanometer, or can you differentiate between 0.01 nanometers, right? So that's the comb that you're putting through. um yeah, so that's so the data that you will work with will be either imaging or will be spectra. But all of that, like, once you get that data, you are essentially trying to get all that information that now Karthik will, I guess, talk about in terms of what to
Right.
do with that light once you get it.
Yeah, so I guess there's three different parts to this introduction that I wanted to give. One was what are you actually measuring, which is basically what is an SED, what is photometry, what's spectroscopy. The second part is what is this light made up of? And the third part is how do you actually perform inference, which is to take an SED and then convert it into some usable physical quantity of interest. So the so I think we covered the what is an SED part. The second thing is where did it go? Was it here? Yeah, is what is it made up of? So broadly, a galaxy is made up for the purposes of this discussion, right? A galaxy is made of stars, of gas surrounding these stars, or just dispersed in the interstellar medium of the galaxy. So just like all the gas that hasn't collapsed under gravitational pressure and started nuclear fusion to form stars yet. And dust, which basically comes from both leftover remnants of the star formation process, but also some other things like shocks from supernovae and uh, really old stars, basically like creating exhaust fumes. Um, so you have light from stars, which is the stellar continuum. You have light from the gas. Now, the gas by itself isn't producing light, but light from stars and from other high energy sources goes, excites the atoms in the gas. And then those atoms, when they de excite, will release radiation. And that's called nebular emission. Nebula just coming from the old word for like a diffuse, luminous source. Then there's light that gets absorbed by dust in high energy. So basically, if you have this thick blue line, that's all the light that comes from stars. But then if you look at the black spectrum, which is what you would actually see, it's less than this thick blue light, right? Which is so some of that radiation is missing. And what's happening is essentially that radiation is being absorbed by dust, and then that radiation is re-emitted at much lower energies. So it essentially takes up some of the UV radiation from stars and re-emits that as infrared radiation. And so that's the contribution of dust. And then finally, a lot of galaxies have these big supermassive black holes in their centers. And the supermassive black hole tends to essentially radiate across a whole bunch of different energies. Let me see if I have a quick plot of yeah. So this is basically one graphic showing, the all the different it's an exploded view of a galaxy, but it's just splitting it up into uh, all the different regions in which the area around a supermassive black hole. So this is just a black hole that's sitting in the center of a galaxy, uh, is accreting material from all the gas and everything that's sort of spiraling into the galaxy and then emitting at a range of wavelengths. So it tends to emit, in the optical, in the X-rays, in the infrared, uh, in the microwave, in radio frequencies. And so not all galaxies have the supermassive black hole, but when they do, you tend to find emission across a whole bunch of different wavelengths. The connection between how light from supermassive black holes and light from the stars of a galaxy correlate is still not fully understood. This is very much an open problem, and there are people working on this right now. But okay, let's go back to this one. So in this picture that I showed, Uh, I'm essentially showing the net emission from all of these different sources, but let's go source by source. So I think the first one we start is the stars, right? Like the stars provide the most useful information, the most amount of useful information, but to get at it, we need to disentangle it from all the other things. So uh, what happens is if you just look at all the emission that comes from the stars, you'll see a spectrum that looks something like this, right? There's essentially, it looks like a combination of many different black body spectra with some extra features thrown in for fun. But the reason this happens is because let's see if I have that picture somewhere. All right, there we go. So there's a relation between the temperature of a star, the lifetime of that star, and the temperature of that star and how its spectrum looks, right? So something that's hotter tends to burn through its fuel faster and be shorter lived. And something that's dimmer tends to take a lot more time to burn through its fuel and be much longer lived. And if you extend this, something that's hotter is shorter lived, but also peaks in its spectrum at bluer wavelengths, so higher energies because it's burning hotter. And then something that's longer lived tends to peak at the redder end of the spectrum. And so when you go and look at the stellar continuum, which is a sum of all of these different, stars of different temperatures and therefore of different ages, you tend to see that there's peaks that correspond to contributions from young, massive, hot stars, some that tend to come from intermediate age stars, and some that tend to come from older stars. And so the really cool thing about this is that if you see or if you manage to isolate the stellar emission from a galaxy's SED, you can then break it down into, okay, how many young stars are there in this galaxy, how many intermediate age stars are in this galaxy, and how many old stars are there in this galaxy. And then you can do a bunch of things with that information. If you want to say, what is the total mass of this galaxy, then all you need to do is, multiply the number of young stars by the mass of a young star, add that to the number of intermediate age stars multiplied by the mass of an intermediate age star, and then keep doing this until you have summed up over all the different stars. And now you have the stellar mass of the galaxy. If you want to figure out the star formation rate, the rate at which this galaxy is forming new stars, then all you need to do is look at the amount of light that's coming from these youngest stars, right? And that will tell you like how many new young stars are being produced per amount of time, because if the galaxy wasn't actively forming stars, you wouldn't see any light in this part of the spectrum, right? It will just look extremely quiescent. So for that, I think I had yeah. So this is basically on the x-axis, you have amount of time looking back into the past. And on the y-axis, you have star formation rate, which is the rate at which it's forming new stars. And you can see as you change the star formation rate, how you're changing the amount of light that's coming in, especially at these blue wavelengths, right? So if you're able to have a filter, let's see if I can annotate this. Yeah, if you can put a filter here, right, to measure the amount of flux, and you can put a filter here to sort of measure the sort of stable amount of flux that's coming from these older stars, right? So you have one filter, one measurement here and one measurement here, uh, wherever. Then that allows you to, I'm sorry for the bad drawings, but that allows you to tell how many new stars are being produced.
Yeah, that's a really cool graphic, Karthik.
Thank you.
Yeah. So again, if can I recap a little?
Yeah,
Just
yeah.
yeah.
Wait, so I just wanted to
Do you want
quickly go
to?
through the other things without
Yeah.
going into too much detail.
Oh yeah, yeah,
Uh,
sure.
where did it go? Okay, yeah. So, so that the stellar continuum contains the most information about the actual stars in the galaxy. If you can isolate that, you can basically say how many young, medium age, old stars are in the galaxy, and therefore estimate things like how massive the galaxy is and how many new stars it's forming. The second part is, and so this is how the stellar continuum looks for stars of different ages. right? So blue is the youngest stars, red is the oldest stars. And what you see is actually the sum of all of these weighted by the number of stars in each age bin. Uh, the second part is this nebular emission, which is basically when light from these stars goes through gases in the interstellar medium and ends up ionizing all the different species. The paper has a treatment of sort of all the different ways in which you can ionize the gas. Sometimes you just like make an electron pop out altogether. Sometimes you just excite it to a higher level and it just falls down. Sometimes you just do things like change the spin, and all of these will produce emission lines that have characteristic wavelengths. And so every one of these interactions has like some associated physical mechanism or some cause that can produce it. And so looking at these emission lines lets you, for hydrogen lines, lets you say things about how hot the ISM is, um, or what is the amount of like radiation from different sources that might be affecting it. And in other elements, it can sometimes just tell you how many ions of this other element there are, and therefore give you a measure on the chemical composition of the galaxy's gas. Then there's dust. Dust, as I mentioned, like tends to take light out from the optical and UV and re-radiate it in the infrared. And dust is, it also tells you a lot about the interstellar medium of the galaxy. But if you are in the UV to optical portion, like if you're an optical astronomer, dust is just a problem for you. You don't really care about, doing anything except accounting for it because it's taking away light and making everything harder. But if you're in infrared astronomer, then dust is actually the main thing that you are observing, and you want to understand everything about its geometry and its effects and all of these things. So this is sort of what it looks like. If you have a telescope, you have the actual light from the galaxy, and then you have all of these clouds of dust. So they tend to scatter light and they tend to absorb light. And that essentially like reduces the amount of signal to noise in the optical and UV. And then in those regions, you will then see the same regions as like these massive hot clumps when you look at the same galaxy in the infrared. Right. And then like I briefly mentioned AGN, and I just said that there's a whole bunch of different sources of emission, and that I think would be like a lecture of its own. So we won't go into that in too much detail. But the point is you have light from all these sources.
Mhm.
And when we measure a galaxy spectrum, the next step is to then to try to decompose it into all of its components. And if we care about things like stellar mass and star formation rate, then to try to isolate the stellar continuum and break it down into amount of light coming from stars of different ages. All right, that's my quick spiel. Lamia, do you want to?
Yeah, no, that's great. So I will just hit the main points again
Yeah.
so that you guys, have a recap. So the three main components that you will need to remember for your work is the stellar continuum, the nebular emission, and the dust absorption and emission. Okay. So the stellar continuum, Karthik, can we go to that figure with all the different star
Yeah.
ages?
The etc.
No, the spectra of all, yeah, the next one. Yeah,
Yeah,
there
yeah.
we go. Yeah. So the what you need to remember is that I think we've talked about this, like the younger stars, they are which color? Or let's not actually, let me not phrase it that way. Um, High mass stars, what are their colors?
Blue.
Bluer, and low mass stars are redder, right?
Right.
So high mass stars, they have a higher temperature because the more mass you have, the more fuel you have, and then you burn it at you're just having a party, right? You're going out of control. Live fast, die young. Blue stars, they are the first ones to die. So the blue stars, they live a very short time, right? So
Yeah.
when we are looking at our galaxies, you can see that all the stars, they actually give red light, right? But all the stars don't give a lot of blue light. right? So what you are actually trying to look for is that is there blue light or not? Because red light is coming from pretty much every star, right? So we try to get the ratio between the blue to the red, right? Because if we get a lot of blue, then you know that there are hotter stars that are present in your galaxy, which means that it has had recent star formation because there are still short-lived stars that are remaining, right? They haven't died out yet. If you don't see these short-lived stars, then that means that probably there hasn't been a recent star formation in the last 100 million years or last billion year or so, because if there had been, they would have still been alive. If you don't see them, then they have died out. So the star formation didn't happen for quite a while. So when you hear about like old galaxy versus new versus young galaxy, what we actually mean is that it is that galaxy recently did it form any stars or not, right? When we say old galaxy, we mean that a galaxy that has just not formed a lot of stars in the last 100 million years time, right? So the blue is the one that we're looking for, and you should always look for that blue. If you see some, like a galaxy with spiral arms, lots of blue in on it, then you know that that's likely going to be a galaxy that has formed stars in the recent past, right? Now, Karthik will tell you that the star formation history of galaxy is a much more complex matter and it's not really binary, it's not really young and old. A galaxy you know, may have been born a really long time ago, but it has still formed some stars recently. So do you call it old or do you call it young, right? So what we will say is that has it formed stars recently, right? Is it a star forming galaxy or
Ma'am, I have a question.
yes, Jyoti, go
These
ahead.
are all these are all stellar continuum line, right?
Yes.
But in the SCD, I just have one continuum line. So how am I converting all these lines to one single?
Yes, that's a great question.
So,
Yeah, go ahead.
yeah. Now, broadly, like the short answer is you're summing it all up. So what you're seeing is the summed up light from all the young stars and the intermediate stars and the old stars that are in the galaxy. And that's the hard part. The hard part is to then take the summed up spectrum and notice that the sum is not equal, right? Like in the sense that if you look at a young star, it is going to contribute a lot more in blue wavelengths than it is at uh you know I'm just going to call it blue, green, and red for sake of simplicity, than at a green or a red wavelength. Whereas an old star tends to contribute most at the red wavelengths. And so the trick is to just take that summed up thing and try to split it up into different spectra, so that the addition of all of these component spectra with the correct weights will give you that summed up integrated spectra. And then figuring out those weights is the part where we say, oh, we are trying to recover information about the star formation history of the galaxy. Because the weights tell you, this is how many young stars I need, this is how many intermediate age, and this is how many old stars I need, so that I can sum up the individual spectra and get, this combined thing. Does that make sense?
Yeah,
Yeah.
so I think Kartik will talk about that more in the feeding process part as well. But that is where, a lot of the the meat of the game comes in, right? It's like, okay, are we talking about lots of intermediate mass stars or like, some young stars, a lot of old stars, like where are all these lights coming from?
Right.
So
Yeah, here's another example of where I'm keeping the total amount of stars the same, and I'm keeping the star formation rate also the same. I'm only changing where those stars come from, right? So this T50 that I'm showing sliding across the screen is basically when in time the galaxy forms the majority of its stars. So when the T50 is here, most of the stars are old, and then it's sliding towards younger ages, right? So as this T50 slides towards zero, all of the stars are getting broadly younger, and you can see how the spectrum changes as a result. So the blue light doesn't change at all because we're keeping the star formation rate at T equals 0 constant. And the overall normalization doesn't change much because we're keeping the mass constant. So the only thing we're changing here is how old the stars are, and you can see how that changes the shape of the spectrum. So unfortunately, we only have access to one spectrum for the whole galaxy. So we have to solve this problem of how to break the integrated stellar continuum into all of these different parts. But then that's where all of our fitting stuff comes in.
Yeah. So most of your light is coming from the stellar continuum, right? Like the overall shape of the SED that you see, it's the stellar continuum that is being modified by the other components. So, for example, if you have a lot of nebula, if you have a lot of gas, which are getting, if you have a lot of cold gas, which are getting excited and then are uh, re-emitting some light, then you will have all those emission
Emission line.
lines in your spectra. So your spectra will have lots of lines in them. Whereas if
Yeah.
you don't have, if you're a gas poor galaxy, if you do not have any gas that can be excited, then you will have a spectra that looks more like those red ones, which you see like do not have a lot of emission, like lot of emission lines, but have some absorption features, right? So there are some absorptions that are um, happening
Yeah.
that we will not talk too much about yet because I
Yeah.
want to limit the information we are giving you
Yeah.
at the moment.
Already this is a lot of stuff to
Yeah.
go through.
And then the last thing was the dust, because that does modify your spectra quite a bit, because what dust does is that if you think of like um, if you're looking through a sandstorm, right, you cannot really see the other side because the sand particles are blocking the optical light, right? So this blocks the UV, it blocks the optical light preferentially, and as it is blocking, it's getting heated up. So then that light is re-emitted in the infrared, in the near infrared, in the mid infrared, sometimes in far infrared as well. So what that does overall is that it will change the shape because it will take the light out of the blue, out of the UV, and then bump up your IR, right? So it will overall change the shape of your SED.
Yeah.
So
So
yeah,
here the blue line, for example, is showing a galaxy with a moderate amount of dust. The line up top is where there is no dust or very little dust, and then the line below is when there's a lot more dust. So you can see that all the UV and even some of the optical part of the spectrum just gets much dimmer because of this, but then that corresponding energy ends up getting re-emitted in your infrared.
yeah. So it's conservation of energy, right? Like if you are taking in heat from somewhere, you have to give off that heat somewhere in other parts. So it's taking the light from the UV, but then re-emitting it in the IR. Okay,
Yeah.
cool. Great.
Yeah, and then I guess I'm not going to go into all of these things right now. Okay. Before we get into SED fitting specifically, I think I wanted to share this paper. So I'll put this in the chat as well. I think this is a good paper to have in general. It's it's basically this pedagogical paper talking about how you fit, any model to any data. uh, Specifically focusing on how you do linear fits. How do you fit a line to a bunch of points, given that those points have error bars and measurement uncertainties, sometimes in both the X and the Y direction. I really like this because not only does it have like a really good overall summary of how you do these things, but it also has exercises in it. And so if you have the time, I think just going through this, like for me, this was a big part of how I learned statistics. And I think it was just very useful. So I like spreading it.
Yeah.
But okay. So I put this in the chat if anyone wants to pick it up. But the point is, so okay, we have an SED, we know what it's made of. Now the part is to figure out how do we actually extract these numbers from it. By the way, I realize we are over time already.
Um,
for
I had it till 12:30, so if you have time
okay.
to take
I have time, but I hope all of you all are
okay.
okay. Yeah. If anyone needs to log off, like we are recording this anyway.
Yes.
Yeah. Okay. So we have figured out, we know how to measure the SED. We write our telescope proposal, we get some photometry. And then we know that, okay, in this photometry, if I'm looking in this optical to infrared part, then it's going to be mostly stellar light. And I now want to use that to measure something like the stellar mass. So how do we do it? So the way we do it is we create model SEDs, right? So this is SEDs that we make using our theoretical or empirical models where we know the true answer, so I can make an SED for a galaxy that has a billion solar masses worth of stars and is forming stars at a certain age and has a certain chemical composition and has some amount of dust, all of these things. And then we say that we are going to compare that to our observations, which are the points here. And we are going to figure out some way of saying whether a comparison is good or bad. And for that, we write down something called a likelihood function. So this is basically saying that if I have a line and I want to compare it to a bunch of points, then I just evaluate the value of that line at the x coordinates of each of those points and I compute the mean squared error, right? And so I can minimize that and I can figure out, okay, this value of the mean and intercept of this line is the best match to my model. So the same thing here, if I'm varying just a single parameter, which is stellar mass, I vary that in across the parameter space. And because I'm changing only the overall stellar mass, the only thing that's changing is the whole SED is moving up and down, right? Because all I'm changing is the total number of stars. So I'm taking each of the components of the stellar continuum and multiplying it by a number. And the intensity of the lines is proportional to the likelihood. So basically, a darker line is a better match, and a lighter line is a worse match, just in this figure. So what this is saying is like as I change my stellar mass from like 9.2 to 9.5, it starts out as not being a really good match. Then at some point it peaks and then it starts declining again. And if I look at that peak, that's sort of my optimal estimate for what I think the mass of this galaxy is, just because that's the set of models that best describes the data that we're looking at. So uh, the way we do this in practice is to use some kind of an optimization routine. So you can either say that I'm going to make a grid in the parameter that I care about, and at each value of the grid, I'm going to see how good the match is. And then I'm just going to take the best match, like the coordinate in the grid for the best match, and say that's the correct answer or that's the optimal answer. Or you can do something like Markov chain Monte Carlo, which is where you randomly sample the space and you have some criteria for what the next sample should be, and you keep doing it until you really sampled sort of this area of good likelihood to know uh, not just what the best individual point is, but sort of how uncertain you are about that. So this is for a single parameter. Uh, this is for another parameter. If I don't care about mass, I only care about the amount of dust attenuation. I am sampling over the dust attenuation space, right? And you can see that now the way the models change is actually different. And there are, for very low dust attenuation values, it's not a good match. Sorry, up here. And then for very high dust attenuation values down here is also not a good match. So by sweeping over this parameter space, you're able to understand like what the optimal value is. Now we did mass separately here and then dust separately here. In practice, what we will end up doing is sort of do both of them together. So then like now I'm showing you spectral samples when I'm varying in my model space both the mass and the dust. And so now you can see that there's a lot more of these like funky looking spectra where you've changed both. And so like this really bad match down here is where both the mass is low and the dust is too high, right? And so that's a bad match. And so then you not only get these individual parameter estimates, but you also get this thing called a covariance, which is saying that uh, this is my optimal answer given the data, But an answer where both the mass is higher and the dust is higher is also okay, right? Because if my mass is higher, my overall spectrum shifts up. And then if my dust is higher, just the blue end shifts down. So that's not as bad of a match because I'm sort of canceling out the two effects to get something that looks similar. And then in the same direction, lower dust and lower mass is also good, right? Because then I'm attenuating it less, but then there's also less light to begin with. So this is something that is really useful when we are dealing with actual observations, where it's not going to be these single points, but it's going to be points with uncertainties on them. So when you have an actual observation, it's not going to be like just this point. It'll be this point with some kind of error bar that says, oh, actually, given how long I pointed my telescope at this galaxy, this is the range in which I think the flux density can lie, right? Like this is the actual measurement I've done, but then given the systematics of the telescope, the exposure time, all of these things, this is the range in which it can lie. And so in observations where you have these measurement uncertainties, these covariances are really key because they sort of let you figure out, if my parameter is uncertain, what is the direction in which these uncertainties propagate? Uh, so okay, I think then we go into nitty-gritties of actual fitting, which I don't know how much detail I want to get into for this today. Let's see. Yeah, let's do it here. So broadly, what we're doing is we start with some combination of photometry, which is like these boxes. They are core samples of the spectrum, and spectroscopy, which is something that's finer and like, gives you more detailed shape information, but tends to be less signal to noise. We then essentially compare it with a bunch of different models. And then for each model, we evaluate how likely that model is. Each model also corresponds to some point in physical parameter space. So once we have computed how likely each model is, we automatically get how likely each physical parameter is, just because there is a mapping between the observed SED and each of these things that we're estimating. So the moment we sort of like take all possible models where we vary the dust, where we vary the star formation history, where we vary the metallicity, and we make SEDs for all of them, and we compare each of those SEDs with our observation, then we can go back and say, okay, this is the most likely value for dust, this is the most likely value for metallicity, because those are the ones that best match what we see in terms of the spectrum. And then once we have that, we can then turn that into something like the star formation history or metallicity history or dust attenuation. So I think this part is also a bit more detailed, so I'm not going to go into that, too much. I'd say in this step, like does this sort of make sense overall to you folks? I know that this is we've jumped from like observations to the physics of galaxy spectra to the nitty-gritties of fitting. So it's a lot of different things. Uh, but the basic point I want you to take away today is just that when we want to fit a galaxy spectrum, we use theoretical models that can vary all of these different parameters that I talked about that correspond to the mechanisms by which a galaxy emits light. We vary these things, we compare them to our observations, we evaluate how good that comparison is, and we use that to build something called a likelihood function, which essentially says, okay, for each parameter, this is the values or the set of values or the range of values that are most consistent with the observations, right? And so when we do this in practice, we end up with, let me see if I have a corner plot to show somewhere. Yeah, this one's fine. So we end up with like something that looks like this thing in the bottom, which is often called a corner plot in the literature. So this says like, oh, there are these 4 parameters that I'm trying to estimate from a galaxy spectrum. 3 of these correspond to the star formation history, and one is about the metal content. We don't need to worry about the actual values for now. but then these are the optimal, values that we have obtained for each of these parameters, and then these are the covariances. So essentially, like, if I increase or if I increase one and decrease the other in this direction, then that's still consistent with the observations. But for all the others, it doesn't really matter. Like, they're uncorrelated from each other. And then this is how, like, a fit to a galaxy spectrum looks like. So this is another corner plot where from this fit, they have obtained basically the amount of stars in the galaxy, which they're calling mass formed, and then the star formation rate at the time of observation. And they're also looking for redshift, which is how far away the galaxy is from us. That's another thing you can constrain. Okay, I think I'm going to